Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of NEET preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we're dealing with moving charges and magnetism. This is the fourth chapter in the grade 12 syllabus for physics in CBSE. Let's look at our first question. 4 wires, each of length 2 meters, are bent into 4 loops P, Q, R, and S, given below, and then suspended in a uniform magnetic field. If the same current is passed in each, then the torque will be maximum on the loop P, Q, R, or S. Let's look at our question. Well, we have a square, couple of rectangles, and a circle, all of which have the perimeter or circumference as 2 meters. Now, when it comes to the area of the loop, we know that all of these have the same perimeter. So among shapes that have the same perimeter, the circle has the maximum area. And the torque on the loop is directly proportional to the area. So for the same perimeter and the same amount of current, the torque will be maximum in the loop, which has the maximum area, which in this case is loop S because it is a circle. P, Q, and R are rectangles and squares which do not have this maximum amount of area. The square has the maximum amount of area when it comes among rectangles, but when it is subject to all the figures, then the circle takes center spot. So here the maximum area belongs to the circle because all of these have the same perimeter, and since they have the same current passing through them, the torque will be also dependent on the area of the loop. So option D, loop S, is the right option. Next question. A square coil of side A carries a current I. The magnetic field at the center of the coil is. So in order to solve this question, we notice that we have 4 sides to this square coil. So what we do is we consider each side as one straight current carrying conductor. So therefore the total magnetic field at the center O will be equal to 4 times the magnetic field of each side, since one side is a square conductor. So B of side will be the magnetic field produced by a straight current carrying conductor, which has the formula 4 times mu naught I divided by 2 pi into the distance. Now we know that the side is A and the center lies at the position A by 2. So the value of R will be A by 2. And since the magnetic field comes from both the top and the bottom of the conductor, we will write sine pi by 4 plus sine pi by 4 in the bracket. Okay, so now let's write it down. So 4 into mu naught I divided by 2 pi times A by 2 into the value of sine pi by 4 is 1 by root 2. Sine 45 is 1 by root 2. 1 by root 2 plus 1 by root 2. Now what we do? Let's write it as 4 mu naught I divided by 2 pi times a by 2 into 2 by root 2. So in order to solve this, let's multiply root 2 on both the numerator and the denominator. So we'll get for mu naught I divided by 2 pi times a by 2 times 2 root 2 divided by 2, which again becomes root 2. So we have root 2 there, and then we can cancel the 2 and 4. So we have 2 here. So therefore, the final answer will be 2 root 2 mu naught I divided by a pi. Notice that there are some steps here, but the final answer here will be 2 root 2 mu naught I divided by a pi. And which of these is the right option when it comes to that? Well, 2 root 2 mu naught I by a pi is the same option as option D. So option D will be our right option. And the reason and the way we did is we considered each of the square sides as one straight current carrying conductor. And we used the formula for magnetic field of a straight current carrying conductor at a point. So that's how we got to 2 mu naught I divided by a pi. Option D is the right option. Next question. A charged particle moves through a magnetic field in a direction perpendicular to it. Then which of these remains unchanged? Is it velocity? Is it speed? Is it direction? Is it acceleration? So over here, we use the formula for magnetic force. Magnetic force is equal to Q times V bar cross B bar. Here V stands for velocity. Now, this particular multiplication is called a cross product. So for force to have the cross product of velocity and magnetic field, this will imply that force is now perpendicular to the magnetic field. So when force is perpendicular to the magnetic field, suppose we have V and then we have F in this direction. So we find that there is virtually no change in the magnitude of velocity. So magnitude of velocity remains the same, but the direction changes. So therefore, since the direction changes, option C remains incorrect. And we can also discard options A and D because of the fact that both velocity and acceleration have direction. So velocity as a quantity gets changed, but the magnitude remains same. The reason why is when we have the force of a magnetic force acting perpendicularly, you form circular motion. And in circular motion, the velocity and acceleration always changes with respect to direction, but the magnitude of velocity, which is speed of the particle, remains unchanged. So option B, speed of the particle remains unchanged, is the right option. Next question. Wires 1 and 2. They carry currents I1 and I2 respectively, and they are inclined at an angle Q to each other. What is the force on a small element dl of wire 2 at a distance of r from wire 1, which is shown in the figure, due to the magnetic field of wire 1? So we have a figure here. We need to find the magnetic field at point P. So at the point P, we will have magnetic field B is equal to mu naught I divided by 2 pi r due to the straight current carrying conductor I1 into current, the conductor I1 is at 0 degrees with the reference, so it will be cos 0, and then plus cos, the value here is given as theta. Cos 0 is 1, So therefore, B, it will be equal to mu naught when it comes to the current I1, it acts at 90 degrees, so therefore cos 90 is equal to 0. So this quantity gets cancelled. So our magnetic field is mu naught I divided by 2 pi r into cos theta. This is the magnetic field. Now what we do, we find the force due to the length dl of wire 2 at wire 1. Now this force, using the Biot-Savart's law, B1 is dF is equal to I2 times dl times B times sine 90 degrees. So I2 and dl stays the same. The magnetic field is written as mu naught by 2 pi into I1 divided by r. That is the magnetic field. And then sine 90 is 1. So therefore, we have mu naught by 2 pi into I1, I2 divided by r times dl. Now, the magnetic field also has a cos theta in it, so dl times cos theta. So the magnetic field is mu naught by 2 pi into I1 by r times cos theta. So therefore, this quantity, mu naught by 2 pi into I1, I2 by r times dl times cos theta, this will be similar to option C. Now over here, the r goes into the mu naught side, so it becomes mu naught by 2 pi r and then I1, I2 dl cos theta. But anyways, it still says the same. So option C is the right option. In options A and B, it's the ratio of the angle is different. It's tan and sine. That's incorrect. And in option D, it is 4 pi r and then there's a sine theta. So both these aspects make option D incorrect. The right answer is option C. And we use the Biot-Savart's law in order to get it. So first we found the magnetic field at the point P, and using that magnetic field, we found the force acting on D1 on the wire 1 due to the length dl. So then we, without integration, we got this value. So this is the right option, option C. Next question. If we double the radius of a coil, keeping the current through it unchanged, then the magnetic field at any point at a large distance from the center becomes approximately. So it's either double, 3 times, 4 times, or 1 by 4. So let's draw the case here. So we have a circular coil with R. We don't know the number of turns. It may be 1, it may be many. So let's have number of turns is N. And then we need to find the magnetic field at a distance x away from it. So magnetic field on the axial line of a uniform circular current carrying coil, it is equal to mu naught N into I times R square divided by 2 into R square plus X square, the whole raised to 3 by 2. This is a derived formula. Now, in this scenario, we know that X is way greater than R. Notice. So therefore, in the denominator, this gets ignored. So therefore, B will become mu naught N I R square divided by 2x cubed, which is 2x square raised to 3 by 2. So the square and by 2 gets cancelled, so 2x cubed. So B will be equal to mu naught Ni divided by 2x cubed into R square. So therefore, using that formula, which let me write it down here. B is equal to mu naught Ni divided by 2x cubed times r squared. So magnetic field is proportional to r squared. So therefore, when r gets doubled, let's write down that r dash as 2r. So the b dash, again, will be proportional to r dash the whole square. That means b dash is 2r the whole square. So that means b dash is proportional to 4r squared. Now now the original magnetic field B is proportional to r squared, and this b dash is actually proportional to 4r squared when r becomes 2r. So therefore, when the radius gets doubled, the magnetic field becomes 4 times larger. And which of these options is the right one? Option C. Because the magnetic field at any point at a large distance becomes approximately 4 times when we double the radius of the coil. Now over here, the important thing to note is that while in the denominator the radius gets nullified, in the numerator it still exists, and it's that ratio of the radius with the magnetic field that we use in order to find out the magnetic field at any point at a large distance from the center when we double the radius of the coil, which is 4 times because B is proportional to r squared. Option D, 1 by 4, will be incorrect. For that, it will have to be B proportional to 1 by r squared, but the denominator 1 gets cancelled, so that's incorrect. For 3 times, it will have to be root 3 or something, so that is incorrect. And double, well, it has to be B proportional to r, so that 2r makes that 2B will be proportional. So that means that B dash will be proportional to 2r, so therefore the double happens. However, here it's B is proportional to r squared, so 4 times is the right option. Let's look at this question. A portion of a conductive wire is bent in the form of a semicircle of radius r as shown below. At the center of the semicircle, the magnetic induction will be. So in this diagram, we have 2 segments of the wire which are straight and 1 segment which acts as a semicircle. So the magnetic field of straight line will usually act like this. So therefore, there is no component of the magnetic field of the straight carrying wire at O, because the component will be B times sine 0 or sine 180. So that means there is no component of B of straight conductor at the point O. Now the only component that comes here is the component of the semicircle. So the magnetic field at the point O is the magnetic field due to a semicircle. Now we know that a semicircle is basically half of a circle. So the magnetic field will also be the same. So it'll be half of B circle. Now in this semicircle, we have a radius small r. So the radius is small r. So now what we do is we put in the formula. The formula is 1 by 2 times. The formula is mu naught I divided by 2 times r. So it becomes mu naught I times 2 times 2 divided by 2 times 2 is 4r. So this is the magnetic field at the point O. So options A and B are incorrect. Now, how do you choose between C and D? Now, for magnetic field, the SI unit is always Tesla. Now, in this scenario, we consider the current to be in amps, which is the SI unit, and the radius in meters, which is the SI unit. So therefore, option D will be the right option. Now, our final question. A coil of circular cross-section having 1,000 turns and 4 centimeter square face area is placed with its axis parallel to a magnetic field, which decreases by 10 raised to minus 2 Webers per meter square in 0.01 seconds. The EMF induced in this coil is. So let's write down the quantities that we have. N is 1,000. Now the area is given as 4 centimeter square, so that means 4 into 10 raised to minus 4 meters square, and delta B, which is the decrease in magnetic field, that is given as 10 raised to minus 2 Webers per meter square, and the time is again 0.01, so we can write it as 10 raised to minus 2 seconds. Now let's look at the EMF. Well, EMF induced in the coil, which is E, is given as minus change of flux with respect to time. So change of flux with respect to time is the EMF. And the reason why it's negative is because both of them have different directions. So change in flux, that is delta B by delta T times N times A times cos theta. Now, here it says that the axis is parallel to a magnetic field, so therefore theta will be equal to 0. So therefore we have N, which is 1,000, times delta B, which is 10 raised to minus 2, divided by the time again, which is 10 raised to minus 2, times 4, times 10 raised to minus 4, times cos 0, which is 1. So therefore we'll have 1,000 times 4 into 10 raised to minus 4. So 1,000 is 10 raised to minus 3. I mean 10 raised to 3 actually, not 10 raised to minus 3. So we'll have 10 raised to 3 minus 4. That'll be 10 raised to minus 1. So therefore, we will have the value of EMF is equal to 4 times 10 raised to minus 1 volts. So that means 4 into 1 by 10, so that is 4 by 10, so 0.4 volts. Now 0.4 volts can be written as 400 millivolts, and 400 millivolts is option A. Therefore, option A, 400 millivolts, is the right option. Options B, C, and D are incorrect. D is incorrect because the unit is different. If it was 0.4 volts, then D would be correct as well. 4 MV will translate to 0.004, which is not the value given, and 200 millivolts will be 0.2 volts, which is also not the value given. The value that we got is 0.4 volts. That is 400 millivolts. And that concludes this webisode on NEET preparation. Now we have a lot of episodes on NEET preparation. If you want to access our educational content, then don't forget to click the playlist. Click the link of the playlist in the description down below. You'll have access to many chapters of NEET preparation. And if you do want to access more of our useful and interesting content, you can also subscribe to our channel, Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.